Hi, and welcome to this section of the Advanced Calculus 2 tutor. And in this section, we're going to cover the topic of arc lengths in parametric coordinates, or in parametric equations, okay? So let's stop and think about where we've been and where we're going, because it helps to get the big picture. A few sections ago, we talked about the topic of arc length, which was just telling you how to integrate a function so that you can actually find the length of that function. And then we found an equation that talked about the surface area of a function that's been rotated about the x-axis, and that also involved arc lengths, and using that we kind of built on that to find a relation there. Then we switched gears and talked about how to write functions in terms of parametric equations, which are just equations for x and for y separately, in terms of the third variable, usually called t. T for time, okay? So you have an equation for x and an equation for y. We talked about that. Now this section is going to be the arc length formula in terms of parametric equations. So this section exactly mirrors the section on arc length. So go back there and read that and understand that if you have already watched it. But this is doing exactly what that function does, and exactly what that section does, except the equations here are going to apply to systems that are defined in parametric equations. So the concept is the same. Finding the length of an arc is exactly what we're going to do. It's just that now the equations are not f of x, they're x of t and y of t. Parametric equations, okay? So recall that we found a function in Cartesian coordinates. The length, the arc length of that function was an integral from a to b, okay, of the square root of 1 plus f prime of x, which is the derivative of x squared, dx. That's what we found before. We take our function of x, we take the derivative, we square it, we put it in here, and we integrate from a to b along x, and that is the length of that function. Now we want to find an equivalent expression in terms of parametric equations where you don't have f of x, you have x of t, some variable t, and y of t. So obviously this thing's going to look a little bit different, but once we know what it looks like, it's going to be applied exactly the same way to find the arc length. We're just going to plug it in there and do the integrals, okay? So this can also be written as the integral of a to b, just to kind of make it clear, the square root of 1 plus df, or dy, dx squared. Same thing. dy dx, f prime of x is really the same thing, dx. Okay? All right. Now, what we want to do is we want to find an equivalent expression, okay, when the function is not given in terms of f of x, it's given in terms of x of t and y of t. Or it could be any variable here, but we usually call t. So what we're going to have is, draw a little picture, okay? What we're going to have is, we're going to have some function. Let's say it goes up like this and it goes down, whatever this function looks like, okay? This is x and this is y, okay? And we want to find the length of this function, and if this function were f of x and defined in terms of an f of x, we would simply put it in here and get the answer. But let's say this function's not defined in terms of f of x. It has x of t, defining the x-coordinate, and y of t defining the y-coordinate, just as we talked in the last section on parametric equations, okay? So we want to find the arc length, okay? So what we're going to do is we're going to do something very similar to what we did before when we derived the arc length the first place. We're going to look at 2 points, okay? And this point is going to be called P, and I'm going to call him P sub I, just because he's the ith point along here. And this point, which is very close, but not quite on top of him, he's going to be called P sub I minus 1. And all that means is, this is fancy